Now, autoregressive processes and moving average processes, of course, are tools on their own, but they can actually be combined in order to create a bigger model that might have more explanatory power on our data. So an ARMA PQ process, where P stands for the order of AR components and Q for MA components, so is given by equation in here. So again, the given value of process Z is a linear combination of its regressed values, so that's the AR part, and then a linear combination of the white noises, and then there is the white noise for the current value. So an example trajectory of ARMA 1 process is given in here. Now, as we have seen before, the autocorrelation function of AR part may not be very straightforward to read. That's why we also use so-called partial autocorrelation. So that's the one which corrects regular autocorrelation for the effects of the intermediate values. So it kind of cancels out how those specific values would be influencing that relationship that we are looking at here. And so partial autocorrelation has similar explanatory power on autoregressive processes as autocorrelation has on moving average processes. So if you recall, for moving average process, we had this theoretical look of our autocorrelation function. For instance, if it's MA3 process, then we would expect 3 non-zero values here, and the rest would be 0. That's in theory. Of course, when we have sample data, it may not be ideally that case, but we would have 3 prominent lags in here, and the rest would be insignificant. So then, if we were talking about AR process, and of order 3, then partial autocorrelation function would look like that. So we would be looking at sample PACF here. And it's the autocorrelation and partial autocorrelation that gives us the first hint which model order we should use for a particular process. So then if we think of ARMA modeling in general, what belongs to the steps is that first you study seasonality of your data and probable trend. Then if needed, if those features are identified, then you should perform time series decomposition. Then once you remain with the irregular series, you should test it first for stationarity, because non-stationary series cannot be modeled with ARMA. And the two most common stationarity tests available are Dickey-Fuller test and this KPSS test, and they are also both available in MATLAB. In case it turns out that your data is not stationary, you may need to perform differencing. So for instance, if you test your irregular IT series and you find that it's non-stationary, you should be studying then IT minus 1 series. So this one, normally one differencing is actually enough to turn non-stationary series into stationary. Sometimes you have to do it twice. So again, if IT was not stationary, then try differencing, and most likely this will give you, if we call it DT for differencing, so this will give you a stationary series to work with. And then you move on to plotting autocorrelation and partial autocorrelation function in order to identify the possible model order. So for instance, if we had a combination like this, that could mean MA3 process. If we had combination like this of ACF and PACF, that would mean AR2 process, because there are 2 prominent lags on PACF. But you may also have a combination like these two, and that would indicate that you might need to use ARMA 2-3, because AR is 2 and MA is 3. And truth be told, choosing model order is very subjective. Once you are given sample data, the autocorrelation and partial autocorrelation can be very difficult to actually identify what they are. So here is an example where the true model was ARMA 2-1. And so you can see that now this upper MA, it behaves a bit like a wave. So that makes it very hard to identify what is the underlying MA process. On the other hand, for partial autocorrelation, we have 1, 2, 3, perhaps 4 lags which have values going beyond the significance level. However, it's the second one that is the biggest by value. So this could give you a hint that maybe the actual order in here is 2 for AR process, but you could as well go as far as estimating AR 3 or 4. And then if you are not certain of the model choice, like this one is very difficult, so you could either just consider MA1 or go up to MA5, for instance, or at least MA3, because this third one is relatively significant. So when you don't know what to do, you can overfit. So you fit a bigger model on purpose, and then you check the coefficients that you have obtained. So now the original values in our ARMA that I have generated were 0.6 and minus 0.7 for AR1 and 2, and then for MA component was 0.3. Now, when I have fitted a bit too big model by adding 2 extra MA components, you can already judge from these values, especially the second one, that it's not fully relevant in this model. And if we go beyond that, you can see now that these all 4 are insignificant. So this is a bit like a brute force way to decide on the model order. The second, more formal way is using so-called information criteria. So information criteria are measures of the relative quality of statistical model for given data, and information criteria provide means for model selection. The main idea is that they provide trade-off between goodness of fit of the model and then the complexity of the model. It is founded in information theory, so it offers a relative estimate of the information lost when a given model is used to represent the process that generates the data. So the 3 information criteria used in Box-Jenkins model or ARMA model that we have discussed so far are Akaike information criteria, commonly denoted as AIC, then Bayesian information criterion, BIC, and then Hannan-Quinn information criterion. So the first one, Bayesian, also known as Bayesian-Schwarz information criterion, is given by this formula. So in here we have K as the number of parameters in the model, N is the number of observations that we have, and then L is the maximized value of likelihood function. So the idea is to minimize this one, because we are maximizing L, but since it's with a negative value, then we want to minimize this overall. So also we want to minimize the number of parameters used in our fit. Akaike information criterion is given by this formula. So we take into consideration how many parameters our model has, and then how good is the fit by maximizing the likelihood function. So information criterion should be minimized because likelihood is maximized, but it's with negative value. So we tend to look for a minimal value of the whole information criterion. Also, number of parameters is with a positive value. So that's where also we intend to minimize. So in this way, this information criterion rewards goodness of fit by taking into consideration the likelihood, but also penalizes the use of too many parameters. And finally, the Hannan-Quinn information criterion is a bit more complicated. Now, RSS is the residual sum of squares, so it's the difference between our fitted ARMA model and the data. So we drop here the likelihood function, but we still want to minimize this value because we would like to minimize the sum of squares and also minimize the use of parameters. So once again, if you're not certain which model should be used, what you can do is run a whole combination of models, for instance, ranging from ARMA 1001, so the smallest, and then up to, for instance, ARMA 334455. That depends really on the autocorrelation function look. If it doesn't seem to make sense to include higher orders, of course you shouldn't do that. But if there is uncertainty, you're not sure, then it's easiest if you run all the different combinations from this range and then choose the model which has the information criteria minimized.